Hello there, and welcome back to Cosmic Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're embarking on a truly mind-bending journey, one that asks a question almost everyone has pondered at some point, perhaps late at night staring at the ceiling, or during a long drive when your thoughts drift to the infinite. What if there's another you? What if, just beyond our perception, there are other versions of reality, unfolding simultaneously, running on slightly different tracks, or even entirely different rules? Yes, tonight we're diving into the wonderfully weird, yet surprisingly grounded in science, world of parallel universes. It's a concept that, at first whisper, sounds like pure science fiction, a staple of comic books where caped heroes leap between dimensions with casual ease. The plot device in blockbuster movies where alternate realities are just a bad decision or a malfunctioning portal away. We've seen countless cinematic depictions. The world where dinosaurs never died out. The reality where you married someone else. The timeline where a fleeting moment of hesitation led to an entirely different destiny. These stories feed a deep human fascination with what if, allowing us to explore the roads not taken, the lives not lived. But what if this fantastical idea isn't just the product of imaginative screenwriters or ambitious novelists? What if it's not so far-fetched after all? What if it's hiding in plain sight, woven into the very fabric of existence, a silent hum just beneath the threshold of our everyday awareness? The very notion of another universe challenges our most fundamental assumptions about reality. We live in this universe. We experience this moment. The sun rises here, the coffee smells like this, and our memories tell us what happened in our past. Our senses confirm a singular, coherent reality. But what if that coherence is just a perception, a limited bandwidth, or simply one thread in an unimaginably vast tapestry? What if our single linear experience is just a tiny, localized expression of something far grander and infinitely more diverse? The scientific pursuit of parallel universes isn't born from whimsical daydreaming, but from serious attempts to reconcile inconsistencies in our understanding of the cosmos, to fill in gaps that our current models can't quite explain. It's born from mathematical equations that seem to whisper of more, from cosmic observations that suggest a deeper architecture, and from the very nature of quantum mechanics itself, which paints a picture of reality far stranger than we could have ever conceived. Consider for a moment the feeling of decision. Every single day, from the trivial to the profound, we make choices. Do you wear the blue shirt or the green one? Do you turn left or right at the intersection? Do you speak up or stay silent? Each choice seemingly leads to one outcome, solidifying into our lived experience. But how many times have you looked back at a pivotal moment, a fork in the road, and wondered, with a wistful sigh or a pang of regret, what if I had chosen differently? That nagging question, that echo of an unlived possibility, is a very human experience. What if isn't merely a fleeting thought, a mental exercise, but a genuine glimpse, a faint, almost imperceptible tremor of a reality where that other choice did materialize? Where the blue shirt led to a chance encounter, or the left turn revealed a hidden gem, or speaking up changed the course of your day, your week, your life, in ways you can't even imagine here. This isn't about magical thinking. It's about following the logical, and sometimes illogical, conclusions of some of our most robust scientific theories, before we gently unspool the threads of these other worlds, before we explore the mind-bending implications and the startling theoretical evidence. I'd love to know, where in this universe are you listening from tonight? Are you in a bustling city, the distant hum of traffic a lullaby? Or in a quiet countryside, the rustle of leaves against your window pane the only sound? What time is it for you right now? Is it the deep stillness of late night, or the soft glow of dawn? And what little decision did you make today, perhaps so insignificant you barely registered it, that you sometimes wonder, what if I'd done something else? Maybe you chose tea over coffee, or walked a different route to the shop, or simply picked up a book instead of watching television. A video about parallel universes. And here we are, each of us on our own unique path, on our own specific timeline, perhaps unknowingly brushing against countless other versions of ourselves, each version having made a different, equally valid choice in their own unique slice of the clock. It truly is quite fitting, isn't it? This journey into the multiverse isn't about escaping our own reality, but about understanding its potential depth and breadth. It's about stretching our minds beyond what's immediately apparent, beyond the confines of our familiar perceptions. It's about embracing the idea that the universe, in its boundless complexity, might be far more imaginative than even our wildest dreams. This exploration of parallel worlds can actually be deeply grounding. By considering the vastness of possibility, it can make our own singular reality, this moment, this breath, feel all the more precious, all the more unique. If there are countless universes where things happen differently than our experience, our particular sequence of events becomes profoundly special. It's this one, with all its imperfections, its joys, its sorrows, its specific shade of blue dot, if you find this cosmic contemplation soothing, if the thought of infinite possibilities brings you a sense of calm, if the intrigue of these other realities gently nudges you towards slumber, or if this is just a nice way to unwind after a long day, I'd be ever so grateful if you gave the video a like. And perhaps, if you feel inclined to continue these sleepy scientific voyages, consider subscribing to Cosmic Sleep. It helps this little corner of calm reach others who might need a peaceful pause too, who might also be pondering the universe's great mysteries as they drift off to sleep. We're building a quiet community here, a haven for curious minds seeking both knowledge and tranquility. Now, I do hope this isn't so fascinating that it keeps you awake, buzzing with questions and cosmic wonder. But if it does, well, at least you'll have learned something truly profound about the fabric of existence, about the astonishing potential of reality itself, before you drift off. And perhaps, even in wakefulness, the gentle hum of these possibilities will serve as a unique kind of lullaby. So, settle in, really slow your thoughts down, let your muscles relax, and let your mind expand to accommodate wonders that defy easy comprehension. And let's begin, because somewhere between what is, what was, and what might have been, somewhere in the vast, whispering silence of the cosmos, lies the profound and endlessly intriguing story of parallel universes. The story begins not with distant galaxies, but with the very smallest particles, hinting at grander realities just beyond our grasp. It begins with the quantum whisper. When we talk about parallel universes in serious scientific discussions, one of the most compelling, and indeed, one of the most debated ideas comes directly from the strange, fuzzy, and often counterintuitive world of quantum mechanics. This is the realm of the incredibly, unimaginably small, the universe of atoms, electrons, photons, and all the other fundamental particles that make up everything we see and touch. At this microscopic scale, things don't behave at all like the neat, predictable, solid objects we observe in our everyday lives. It's not a billiard ball bouncing off another. It's more like a ghost of a billiard ball existing everywhere at once until you bother to look. Instead of having definite positions or speeds, these tiny particles exist in a state of probabilities. Imagine an electron, a fundamental building block of matter. Before you measure its position, it's not actually in one specific spot. It's not here, or there, or over there. It's more like a cloud of possibilities, a shimmering, indistinct smudge of potential locations. It exists in many possible states, many possible places, all at once, simultaneously. This state of multiple possibilities is known as a superposition. Think of it as a particle that's both spinning clockwise and counterclockwise at the same time, or existing on both sides of a barrier simultaneously. This isn't just a quirky analogy. It's what the mathematics of quantum mechanics tells us, and it's been repeatedly confirmed by experiments. Now, here's where the mystery and the idea of parallel universes truly begins. The famous measurement problem in quantum mechanics asks, if a particle exists in all these possible states at once, what happens when we observe it? What happens when we interact with it in a way that forces it to show us a definite property? According to the traditional Copenhagen interpretation of quantum mechanics, it's only at the moment of observation or measurement that this cloud of possibilities suddenly, instantaneously, and seemingly magically collapses into one definite outcome. The electron decides on a single location. The coin chooses to land heads. The cat in Schrodinger's famous thought experiment suddenly becomes definitively alive or dead. The other possibilities simply vanish like smoke. But why does it collapse? What causes this transition from a fuzzy probabilistic reality to a solid, singular one? And where do all those other possibilities go? This question has puzzled physicists for nearly a century and remains one of the deepest conundrums in science. But here's where it gets really interesting and where parallel universes enter the scientific stage. What if the cloud doesn't collapse? What if, instead of choosing one reality and discarding the others, the universe simply, elegantly, and endlessly splits? This is the core idea of the many worlds interpretation, MWI, first proposed by a brilliant but initially overlooked Princeton University doctoral student named Hugh Everett III in his 1957 PhD thesis. Everett, working under the renowned physicist John Wheeler, found the idea of a collapse unsatisfying and unnecessary. He reasoned that if the laws of quantum mechanics applied universally, why would they stop applying just because a conscious observer or a measuring device got involved? In Everett's radical yet mathematically consistent view, every time a quantum decision is made, every time a particle's probability cloud encounters an interaction that would traditionally cause it to collapse, the universe doesn't pick one outcome. Instead, it branches. Every single possibility that could have happened, every potential outcome, becomes real in its own separate, independent, and equally valid parallel universe. Let's reimagine the electron. If it could go left or right, it doesn't choose. Instead, the universe splits. In one new universe, the electron goes left, and in the other, a parallel universe, the electron goes right. And in each of these newly formed universes, there's a version of you experiencing that particular outcome, completely oblivious to the other branches. If you flip a coin, and it's in a superposition of heads and tails, the moment it lands, and you observe it, the universe branches. In one universe, it lands heads, and the version of you in that universe sees heads. In a parallel universe, it lands tails, and the version of you in that universe sees tails. Both outcomes are equally real, simply occurring in different, now separated, realities. This isn't about the universe duplicating itself in some inefficient, wasteful manner. It's more like it's continuously differentiating, like a vast, ever-branching, constantly growing tree. The trunk is the past, and every quantum interaction, every measurement, every tiny bit of uncertainty that gets amplified to a macroscopic level represents a new fork, a new branch, a new twig. You, me, this room, the very planet we're on, the entire cosmos. We are all just one tiny, singular twig on an unimaginably enormous cosmic tree, with infinite other twigs constantly branching off with every single quantum event, every plunk, moment, every interaction that could have had multiple outcomes. What does this mean for your daily life? It means that every decision you've ever agonized over, Every path not taken, every choice you've considered and discarded, did happen in some other reality. Somewhere out there, existing in a parallel branch of the universe, there's a version of you who took that job offer, who married that other person, who decided to study a different subject, who remembered to water their plants last week, who didn't hit snooze this morning, or who chose the blue shirt instead of the green one. Every single tiny difference, every fluctuation, every moment of perceived randomness could be a branching point. It's a deeply strange, almost overwhelming thought to truly contemplate. It means your existence isn't a single, linear narrative, but a continuous series of divergences, an infinite fan of possibilities. But from a purely theoretical standpoint, MWI offers a compelling solution to the measurement problem by simply saying all possibilities are realized. The wave function never truly collapses. Instead, the universe itself evolves into a superposition of distinct, non-interacting branches. It's just that we, being observers confined to a single branch, only experience one of them. We are, effectively, blind to the infinite other yous, experiencing their equally valid realities. This interpretation is not universally accepted within the physics community. Its critics often cite its lack of falsifiability. How can you test the existence of universes you can never interact with? And its extravagant ontological cost. Why propose an infinite number of universes when a single one seems complex enough? However, its supporters argue that it is the most straightforward interpretation of quantum mechanics, requiring no additional postulates, like a collapse mechanism. It takes the mathematics of quantum mechanics literally, accepting its predictions of multiple states as genuinely real. While the many worlds interpretation is highly speculative and continues to fuel intense debate, it represents a bold attempt to reconcile the bizarre nature of the quantum world with our macroscopic reality. It suggests that the reality we perceive as singular and fixed is, in fact, just one unfolding story within an unimaginably vast, branching cosmic narrative. It reminds us that even in the most mundane moments, we might be standing at a fork in the road of reality, with countless other versions of ourselves stepping down entirely different paths, all equally real, all equally present in the grand, silent hum of the multiverse. And with that thought, perhaps your mind feels a little softer, a little more expansive, ready to drift into the quiet contemplation of what else might be. The many worlds interpretation, as we just explored, springs from the very tiny, often counterintuitive realm of quantum mechanics, suggesting that countless parallel realities branch off with every quantum decision. It's a fascinating idea, born from the deepest, most fundamental levels of reality. But what about the universe? On the grandest scales imaginable? What about the cosmos itself? Could parallel universes arise not from the splitting of an electron, but from the very birth and ongoing expansion of everything there is? This brings us to a different, yet equally compelling, set of theories: cosmic inflation and the mind-boggling idea of bubble universes. To understand this, we need to gently cast our minds back, not to a specific place, but to a specific moment, or rather, the sliver of a moment, right after the Big Bang. For decades, the Big Bang theory has been our most successful scientific model for the origin and evolution of our universe. It describes how our cosmos began as an incredibly hot, dense state and has been expanding and cooling ever since. But like any grand theory, it had a few nagging puzzles, a few persistent wrinkles that physicists struggled to iron out. Two of the biggest were the flatness problem and the horizon problem. The flatness problem asks, why is our universe so incredibly flat? Not flat like a pancake, but flat in terms of its geometry. Imagine the universe as a vast sheet. It could be curved like a sphere, a closed universe, or curved like a saddle, an open universe, or perfectly flat. For life to exist as we know it, and for galaxies to form, the universe had to be extraordinarily close to perfectly flat at the Big Bang. Any slight deviation, and it would have either collapsed back on itself immediately or expanded too rapidly. For anything to coalesce, it's like balancing a pencil on its tip for billions of years. It seems too fine-tuned to be random. The horizon problem, on the other hand, asks, why is the universe so uniform? When we look out into space, the cosmic microwave background, CMB, radiation, which is the leftover heat from the Big Bang, shows us that distant parts of the universe that could never have been in causal contact with each other, meaning light, hasn't had enough time to travel between them since the Big Bang, actually have almost exactly the same temperature. How did they know to be the same temperature if they couldn't exchange information? It's like finding two untouched parts of a massive desert that are exactly the same temperature, despite having no way to transfer heat or communicate. Enter the elegant, yet still theoretical, concept of cosmic inflation. First proposed by physicist Alan Guth in the early 1980s, inflation offers a powerful solution to these problems. It proposes that the universe, in an incredibly tiny fraction of a second, perhaps from 1036 to 1032 seconds after the Big Bang, underwent an unimaginably rapid, exponential expansion. During this fleeting inflationary epoch, space itself stretched faster than the speed of light. To give you a sense of scale, imagine a region of space smaller than a single atom, suddenly swelling to macroscopic size, or even light years across. In an instant, this wasn't matter moving through space, but space itself stretching, carrying matter along with it. How does this solve our problems? Well, imagine taking that highly curved sheet, our universe, and stretching it enormously. The more you stretch it, the flatter it appears. So, inflation naturally flattens the universe to the near-perfect flatness we observe. As for the horizon problem, inflation suggests that the regions that now appear causally disconnected were, in fact, incredibly close together before inflation. They were in thermal equilibrium, having exchanged information. Then inflation blew them apart, stretching them far beyond each other's causal horizons, but preserving their initial uniformity. It's like baking a giant loaf of bread. The entire dough starts at the same temperature, and as it rises and expands, even distant parts of the final loaf retain that initial uniformity. Now, here's where the leap to parallel universes comes in. If this inflation happened, was it a one-time event? Or is it still going on? Many cosmological models, stemming from inflationary theory, suggest that inflation might be eternal. Think of this inflation not as a single burst, but as a vast, ever-expanding, bubbling foam. This eternal inflation continuously produces new bubbles or pockets of space-time that pinch off from the main inflating background. Each of these bubbles would then stop inflating internally and begin its own Big Bang, forming a separate, distinct universe. Our universe, the one we inhabit and observe, would just be one of these countless bubbles floating in an infinite inflating metaverse, or what's often called a multiv, ERSE. Imagine an endless ocean of this inflating stuff. Here and there, randomly, bits of the inflating background cool down or slow their expansion, forming self-contained bubbles. These bubbles then continue to expand and evolve according to their own internal physics, completely cut off from the inflating space outside and from other bubbles. Each of these bubbles could be a complete universe unto itself, vast and seemingly infinite from within, yet just one tiny, isolated droplet in an even grander cosmic sea. The astonishing implication of this bubble universe concept is that each of these newly formed universes could have its own unique set of physical laws, or at least different fundamental constants. Perhaps in one bubble universe, gravity is much stronger, causing everything to collapse quickly. In another, the electron's charge is slightly different, preventing the formation of stable atoms. In yet another, there might be more than 3 spatial dimensions that have uncurled, leading to a reality profoundly alien to ours. We might even find universes where time flows backward, or where entirely different particles govern reality. We can't see these other bubbles because the space between them is inflating so rapidly that light or any other signal can never reach us. They are, quite literally, beyond our observable horizon, forever separated by the ceaseless expansion of the inflating fabric they are embedded within. This idea of a multiverse arising from eternal inflation helps to address another deep mystery that has puzzled scientists and philosophers for ages: the apparent fine-tuning of our universe for life. Our universe's physical constants, like the strength of the strong nuclear force, the mass of an electron, the precise value of dark energy, or the initial conditions of the Big Bang, seem incredibly, almost impossibly, just right for stars to form, for complex elements to be forged, for planets to exist, and for life to emerge. If any of these values were even slightly different, our universe would be a barren, lifeless place. It's like winning a lottery where the odds are so astronomically stacked against you that it feels suspicious. However, there are countless bubble universes out there, each with a random set of physical constants generated by the varying conditions within the inflating metaverse. Then the fine-tuning ceases to be a mystery. It's no longer surprising that we find ourselves in a universe where life could arise. It's simply a selection effect, often referred to as the anthropic principle. We observe the universe we do, with its specific laws and constants, precisely because if it were any different, we wouldn't be here to observe it. It's not necessarily the product of deliberate design or cosmic accident. It's just a statistical inevitability in a landscape of infinite possibilities. Out of all the bubbles, we just happen to live in one that supports our existence. It's like a fish marveling at how perfectly the pond is designed for it, when in reality, it just happens to live in one of the many ponds where fish can exist. So, the next time you look up at the night sky and you feel that familiar sense of awe and immensity, try to stretch your mind just a little further. Beyond the stars and galaxies that pepper our observable cosmos, imagine an endless bubbling foam of inflating space. And within that foam, imagine countless other universes, each as vast and complex as our own, each with its own Big Bang, its own history, its own unique set of rules. We are, in this grand cosmic vision, simply living on one island in an infinite archipelago, one bubble in a boundless, eternal cosmic brew. It's a humbling thought, a dizzying thought, but one that deepens the mystery and expands the wonder of existence itself. And perhaps, as you drift towards sleep, the image of those distant, unseen bubbles will remind you of the boundless potential that lies not just within our universe, but beyond it. We've already soared through the theoretical quantum branches of the many worlds interpretation and pondered the vast, bubbling cosmic foams of eternal inflation. Now, let's consider a more abstract, yet equally compelling, idea for how parallel universes might exist. What if our universe, the one we experience with its familiar 3 spatial dimensions and 1 time dimension, isn't all there is? What if there are more dimensions, simply hidden from us, or perhaps we're not just in space, but stuck on something within a larger space? This is the fascinating and highly speculative concept behind Brain Worlds. To truly grasp the idea of brain worlds, we first need to briefly touch upon the concept of extra dimensions. For centuries, we've operated under the assumption that our universe has 4 dimensions: up, down, left, right, forward, backward, the 3 spatial dimensions, and time, the 4th dimension. This is the familiar fabric of space-time that Einstein described. But what if this is too simplistic? What if reality, at its most fundamental level, is composed of more. The idea of extra dimensions isn't new. It's a core component of several theoretical physics frameworks, most notably string theory and its more expansive successor, N-theory. These theories propose that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating strings of energy. For these strings to consistently vibrate and create all the particles and forces we observe, the mathematics requires more than our familiar 4 dimensions. It typically suggests 10 or 11 dimensions in total. Now, if these extra dimensions exist, why don't we see them? Why don't we feel ourselves moving in a 5th or 6th direction? One common explanation is that these extra dimensions are compactified, or curled up, to an incredibly tiny scale, so small that they are effectively invisible to us. Imagine a garden hose. From far away, it looks like a one-dimensional line. But if you zoom in close enough, you see it has a second curled-up dimension: its circumference. We live on the surface of that hose, unaware of its tiny, curled-up extra dimension unless we were incredibly small. Similarly, our universe could have extra dimensions curled up so tightly that only tiny strings, or perhaps very high energy particles, could feel them. However, brain world theory offers a different explanation for why we don't perceive these extra dimensions. We're stuck on something. Imagine our entire universe isn't a vast, empty expanse, but rather a brain, a giant, flexible, multidimensional membrane or sheet. This brain isn't floating in nothing. It's embedded within a larger, higher dimensional space called the bulk. Think of it like this. Take a piece of paper. That paper is a 2-dimensional surface, a 2D brain. If you draw a dot on it, that dot exists within those 2 dimensions. Now, imagine that piece of paper is floating in a 3-dimensional room, the bulk. We, as beings living entirely on that paper, can only perceive and move within its 2 dimensions. We can go left, right, up, down on the paper, but we have no concept of into the room or out of the room. We are confined to our 2D brain. Yet there's a 3rd dimension all around us, unseen and unfelt by our 2D senses. In brain cosmology, our entire universe, with all its galaxies, stars, planets, and everything in it, including us, is like that piece of paper. We are confined to a 3-dimensional brain, or perhaps a 3-brain plus time, making it a 4-dimensional brain in a higher dimensional space-time. But this brain itself is floating in a higher dimensional bulk. Crucially, in this model, other universes could exist on other brains, also floating in the same bulk. We might be incredibly close to another universe, just separated by a tiny, imperceptible sliver of a higher dimension that we can't directly perceive. It's not about being far away in our familiar 3 dimensions, but rather being offset in a 4th or 5th spatial dimension. Imagine parallel sheets of paper, stacked one atop the other, separated by minuscule gaps in the 3rd dimension. Each sheet is a universe. The magic, or perhaps the mystery, of this model lies in gravity. Unlike other fundamental forces, like the strong nuclear force, which holds atomic nuclei together, the weak nuclear force involved in radioactive decay, or electromagnetism, which governs light, electricity, and magnetism, gravity is thought to be leaky. While the other forces are generally confined to our brain, gravity, in the brain world scenario, is the only fundamental force that can extend off our brain and into the bulk, interacting with other brains. This leakiness of gravity could offer an intriguing explanation for one of physics' great puzzles. Why is gravity so much weaker than the other forces? If you've ever picked up a paperclip with a tiny magnet, you've witnessed this disparity. A minuscule magnet, a force far weaker than gravity, if you consider the entire Earth pulling down on the paperclip, can effortlessly overcome the gravitational pull of an entire planet. In brain world models, gravity might appear weak to us because much of its strength is diluted or leaking into these extra dimensions and potentially into other nearby brains. It's like a radio signal that gets weaker the further you are from the antenna because its energy is spreading out into a larger space. If gravity spreads into all the dimensions of the bulk, it would naturally appear much weaker on our 3D brain. This theory opens up a tantalizing array of possibilities. Perhaps the energy from a collision between our brain and another could be responsible for the Big Bang itself, a cosmic collision rather than a singular point. Or maybe interactions between our brain and a nearby parallel brain could be subtly influencing our universe, perhaps even explaining the mysterious phenomenon of dark energy, the force that seems to be causing our universe's expansion to accelerate. If another brain is drawing energy or matter away, or exerting a subtle gravitational pull, it could manifest as the acceleration we observe. It suggests that our universe isn't some isolated island, but is part of a grander, hidden architecture. A cosmic stack of pancakes, if you will, each pancake a universe unto itself. Or perhaps, to use another analogy, our universe is a film playing on one screen in a vast multiplex, with countless other films playing simultaneously on nearby screens, all within the same larger building, the bulk. We can only see our screen, but the light and sounds from other films are technically nearby, just not directly perceivable without stepping into the hallway. The beauty of brain world cosmology is that it offers solutions to some of our most persistent cosmological puzzles, such as the weakness of gravity, while simultaneously providing a framework for the existence of parallel universes that are physically very close to us, just displaced in a dimension we can't directly sense. While still highly theoretical and requiring further observational evidence to move beyond hypothesis, the mathematical elegance and explanatory power of brain worlds make them a captivating area of research. It forces us to reconsider the very nature of space, dimensions, and our place within a potentially much larger, more complex cosmic reality. So as you settle deeper into your cozy space, allow your mind to ponder that our familiar reality might just be a thin membrane, a shimmering film, floating within an immense, multi-dimensional expanse filled with other worlds, whispering across the unseen gaps. We have gently drifted through the mind-bending concept of quantum branching, where every possibility spawns a new reality, and we've soared through the vast cosmic foams of eternal inflation, where our universe is but a single bubble among countless others. We even dipped our toes into the abstract idea of our universe existing as a flat membrane, a brain in a higher dimensional bulk. These are all compelling visions of parallel universes existing alongside ours, perhaps inaccessible, but coexisting in some broader sense of now. But what if parallel universes aren't just spatial neighbors, existing in other realms that we cannot perceive? What if they are also temporal ones? What if our universe is just one in an endless series of universes, born, living its cosmic lifespan, and then dying, only to be reborn again, perhaps with slightly different fundamental laws or initial conditions? This is the profound and ancient-sounding concept of cyclic universes. The idea of cyclical time, of an eternal return, resonates deeply within many ancient philosophies and spiritual traditions. From the Hindu concept of yugis to the Buddhist wheel of samsara, humanity has long contemplated the universe as something that endlessly repeats or renews itself. While these are philosophical and religious concepts, modern cosmology, in its own way, has stumbled upon a scientific framework that hints at a similar cosmic rhythm. To appreciate the cyclic universe model, we first need to understand the ultimate fate of our own universe, as predicted by our current understanding of cosmology. For billions of years, since the Big Bang, our universe has been expanding. Galaxies are rushing away from each other. Space itself is stretching, and the cosmos is cooling down. This expansion is currently accelerating, driven by the mysterious force we call dark energy. But what happens next? Our fate, as scientists currently understand it, broadly hinges on the density of matter and energy in the universe. And the behavior of this dark energy got one major possibility, which seemed likely before the discovery of accelerating expansion, was the Big Crunch. In this scenario, if there were enough matter and energy in the universe, the gravitational pull between all the galaxies would eventually overcome the initial outward momentum of the Big Bang. The expansion would slow down, halt, and then reverse. Galaxies would begin to rush towards each other, space would contract, and the universe would grow hotter and denser, eventually collapsing back into an incredibly hot, dense singularity, essentially reversing the Big Bang. It would be the ultimate cosmic implosion, a grand finale where all of existence is squeezed back into an infinitesimally small point. However, the discovery of dark energy complicated this picture. If dark energy continues to dominate and accelerate the expansion, then our universe faces a different, perhaps more lonely, fate, the Big Freeze, also known as the heat death. In this scenario, the universe continues to expand forever, endlessly stretching. Galaxies will drift so far apart that they become isolated islands. Stars will burn out, black holes will eventually evaporate through Hawking radiation, and the universe will become an increasingly vast, cold, empty void, eventually reaching a state of maximum entropy where no energy can be exchanged and no processes can occur. It's a universe dying not with a bang, but with a whimper, freezing into eternal nothingness. But the cyclic model, often called the Big Bounce theory, suggests that neither the Big Crunch nor the Big Freeze is the ultimate end. Instead, it proposes that the Big Crunch isn't a final demise, but a violent rebound, a cosmic reset button leading directly to another Big Bang and a new universe. The cosmos, in this view, undergoes an eternal cycle of expansion and contraction, each Big Crunch transitioning through some unknown physics into a big bounce that seeds the next universe. It's like a grand cosmic breath, inhaling for billions of years, then exhaling into a new expansion. The precise mechanism for such a bounce is still highly theoretical and debated. One idea stemming from brain world cosmology, which we just discussed, suggests that our universe is a brain, and when it expands and contracts, it eventually collides with another brain in the higher dimensional bulk. This collision could generate the immense energy needed to trigger a new Big Bang, effectively bouncing our universe back into expansion. Other theories involve exotic forms of matter or quantum gravity effects that prevent a true singularity, instead causing the universe to tunnel through the Big Crunch, point and emerge on the other side as a new expansion. The implications of a cyclic universe are profound and mind-boggling. It means that events, physical laws, and even conscious beings might re-emerge in different iterations of the cosmos. Could an infinite cycle imply an infinite repetition, where every possible variation of every life, every decision, every historical event is eventually lived out across cosmic eons? If the cycles are truly identical, it suggests a deterministic fate, an endless replay. However, many modern cyclic models propose that each bounce might alter the fundamental constants or initial conditions slightly. This means each successive universe could be subtly or dramatically different from the last. Imagine this. In a previous cycle, a slightly different value for the strong nuclear force meant that carbon atoms were unstable, preventing the formation of organic life. In another cycle, gravity was a tiny bit weaker, so galaxies never properly formed. Our universe, with its perfectly tuned constants that allow for stars, planets, and us, is simply one beneficial outcome of this endless cosmic roulette. This reintroduces a version of the anthropic principle we discussed with bubble universes. We are here to observe this universe because it's the one where we could exist. From a grand cosmic perspective, every past universe and every future universe is, in a profound sense, a parallel universe to our own. They exist in a different cosmic era, separated not by spatial distance or quantum branches, but by immense stretches of time, by the very cycle of expansion and contraction. It offers a comforting, if dizzying, thought that the universe, like a cosmic phoenix, is constantly being reborn, unfolding new realities with each cycle. The death of one universe is merely the prelude to the birth of the next. It speaks to a deep, underlying resilience in the cosmos, an eternal cosmic engine that never truly stops, but simply transforms. This model, while offering elegant solutions to some cosmological puzzles, like avoiding the problematic singularity of a true Big Bang or Big Crunch, also introduces new ones. What drives the bounce? What prevents entropy from accumulating over infinite cycles, eventually leading to a true heat death that would stop the cycle? Scientists are still grappling with these questions, and the evidence for or against a cyclic universe is still being gathered through observations of the cosmic microwave background and the large-scale structure of the universe. But for tonight, as you listen to the gentle flow of these ideas, allow yourself to contemplate the immense rhythm of a universe that might not have a beginning or an end, but is instead an eternal dance of birth, death, and rebirth. Imagine endless cosmic breaths. Each inhale a big crunch, each exhale a big bang, creating universes beyond counting. Your own existence, your very breath, becomes part of this vast, timeless rhythm. And perhaps, as you drift towards sleep, the image of those endlessly cycling universes will bring a sense of profound continuity, a quiet echo of eternity. We've journeyed through parallel universes born from the quantum fuzziness of possibilities, from the ever-expanding froth of cosmic inflation, from hidden dimensions where our universe is but a thin membrane, and from the grand, cyclical rebirths of the cosmos itself. Each of these ideas, in its own way, stretches the limits of our imagination and reshapes our understanding of reality. But now, let us consider the most radical, and perhaps the most purely abstract, idea for the existence of parallel universes. What if the deepest truth isn't about physical space, or quantum events, or cosmic cycles, but about the very essence of existence itself? What if every mathematically consistent structure is, in fact, a parallel universe? This is the profoundly unsettling, yet strikingly elegant, concept of the mathematical universe hypothesis. This idea comes from the brilliant and visionary physicist Max Tegmark, who argues for a profound and fundamental connection between mathematics and reality. His hypothesis posits that mathematics isn't merely a language we use to describe the universe. It is the universe. He proposes that our physical reality is not simply well described by mathematics, but that it is a mathematical structure, a self-existent, abstract entity. To truly appreciate this, let's gently unpack what this means. We use mathematics to model everything from the orbit of planets to the flow of electricity, from the behavior of light to the intricate dance of subatomic particles. Our physical laws are expressed in mathematical equations. When we discover a new law, it often feels like we're not inventing mathematics, but discovering something inherent in the universe, something universal and immutable. The number pi, the concept of a prime number, the rules of geometry, these don't feel like human inventions. They feel like fundamental truths that exist independently of our minds. A triangle, for example, has certain properties whether or not a human ever conceives of it. Tegmark takes this intuition to its logical extreme. If numbers, equations, and abstract logical structures exist independently of human minds, which most mathematicians and philosophers of mathematics would agree they do, in some Platonic sense, then why wouldn't a universe that perfectly embodies a different mathematical structure also exist as a reality? In this view, every possible mathematically consistent structure doesn't just describe a potential universe. It is a universe. Imagine the vast landscape of all possible mathematical structures. Some are very simple, like the rules of basic arithmetic. Others are incredibly complex, like the equations describing quantum field theory or general relativity. Tegmark suggests that our universe, with its particular particles, quarks, electrons, its specific forces, gravity, electromagnetism, its familiar three spatial dimensions and one time dimension, and its precise fundamental constants, is simply one of these countless mathematical structures. It's the specific mathematical pattern that governs our reality. But if this is true, then any other mathematically consistent structure, no matter how different from our own, must also exist as a real, self-existent universe. Consider a universe where space has 5 dimensions instead of 3, or where time flows in multiple directions. Imagine a universe where the fundamental particles are entirely different, leading to entirely new kinds of matter and interactions. Or a universe where the speed of light isn't a constant, or where gravity behaves inversely to the cube of distance rather than the square. As long as these alternative structures are internally consistent and obey their own set of mathematical rules, then they exist, as real as our own. They are parallel universes, not in a physical space, but in a conceptual, mathematical space. This is the ultimate multiverse, reaching the highest level in Tegmark's proposed level 4 multiverse. It's not just infinite copies of our universe, like in some interpretations of the many worlds theory, nor just variations with different physical constants, like eternal inflation, nor just hidden dimensions, like brain worlds. Instead, it's infinite variations of all possible universes, each arising from a different fundamental mathematical structure. We are simply inhabitants of the specific mathematical structure that our consciousness can comprehend and interact with, the one that allowed for our formation and evolution. The implications are truly staggering. It means that there isn't just a universe where you had toast instead of cereal this morning. There are universes where the laws of logic are different, where the concept of a particle doesn't even exist, where time is not a progression, but a spatial dimension, or where the very idea of existence is defined in a way we can barely grasp. It implies a reality of boundless complexity, where literally anything that can be consistently defined mathematically is realized. This hypothesis brings a certain austere beauty to the universe. It suggests that the beauty and elegance we find in mathematical proofs are not just reflections of our minds, but reflections of ultimate reality. It implies a kind of cosmic inevitability. If a mathematical structure can exist, it does exist as a universe. There's no external creator, no random selection, just the inherent self-existence of mathematical forms. Everything we perceive, every star, every galaxy, every tree, every thought, every feeling, is just a manifestation of that underlying mathematical truth, a complex pattern within an infinitely larger mathematical tapestry. The main challenge, and indeed the main criticism, of the mathematical universe hypothesis is its testability. How could we ever falsify or verify such a theory? If all mathematical structures exist, how do we distinguish between a purely abstract mathematical concept and a real universe? Tegmark argues that its strength lies in its ability to explain why our universe is the way it is without invoking arbitrary parameters or fine-tuning. If all possible universes exist, then our existence in this particular mathematically structured universe is simply because this is the one that supports conscious observers like us. As you allow these vast concepts to wash over you, consider the profound shift in perspective. Mathematics, often seen as a tool, becomes the fundamental reality. And within that reality, every conceivable and logically consistent form takes shape as a distinct universe. It's a vision that dissolves the boundaries between abstract thought and concrete existence, suggesting that the universe is far more fundamentally interconnected and perhaps simpler in its core essence than we ever imagined. A universe made of pure, self-consistent logic. And perhaps, as you drift deeper into tranquility, the silent, elegant hum of countless mathematical structures, each a universe, will provide the most profound and unique lullaby of all. We have journeyed far tonight, exploring the most intriguing and mind-bending ideas of parallel universes, the endless branching of quantum possibilities, the foamy expanse of bubble universes arising from eternal inflation, the subtle dance of brain worlds hidden in higher dimensions, the grand cosmic rhythm of cyclic rebirths, and even the ultimate reality of a universe fundamentally made of mathematics itself. Each of these theories, in its own way, offers a glimpse into a cosmos far more vast and complex than our everyday senses perceive. They present elegant solutions to deep scientific puzzles, and they ignite the imagination with boundless what-if scenarios. But as with any truly profound and speculative scientific concept, the idea of parallel universes is not without its robust skeptics. Indeed, many respected physicists and philosophers raise very significant concerns, primarily revolving around a cornerstone of modern scientific inquiry, the concept of falsifiability, why at the heart of what distinguishes a scientific theory from a philosophical idea or a purely abstract mathematical construct lies the principle of falsifiability. For a theory to be genuinely scientific, there must exist, at least in principle, a way to prove it wrong. It doesn't mean it will be proven wrong, but that there must be some conceivable observation, some experiment, some piece of evidence that, if found, would definitively demonstrate the theory to be incorrect. This is what allows science to progress. It's how we refine our understanding, discarding ideas that don't match reality and strengthening those that do. Without falsifiability, a theory risks becoming untestable dogma, a belief system that cannot be empirically challenged. The fundamental challenge with most of the prevalent multiverse theories is precisely this issue. They propose universes that are, by their very definition, fundamentally unobservable and undetectable from our own. If these parallel realities are causally disconnected, meaning no light, no information, no force, no signal can travel between our universe and theirs, how can we ever gather empirical evidence for or against their existence? If they leave no discernible trace, no subtle imprint, no cosmic echo within our own observable cosmos, then how do we move beyond pure speculation? Can we truly call them science in the empirical sense? Or do they, however elegant or appealing, venture into the realm of philosophy, metaphysics, or even pure mathematics that has no empirical grounding? Consider, for a moment, the theories we've discussed. The many worlds interpretation, MWI, posits that other quantum branches exist, but by definition, once a branch splits, it becomes inaccessible to observers in other branches. There's no way for you in this universe to peek into the reality, where you chose tea instead of coffee. Eternal inflation's bubble universes are separated by vast, continually expanding voids of inflating space, preventing any interaction or observation. Brain worlds might be incredibly close in a higher dimension, but we are confined to our own brain, unable to perceive the bulk or the other brains within it, save for the elusive effects of gravity. Cyclic universes occur sequentially, so a past universe is gone, and a future one hasn't arrived. And the mathematical universe hypothesis asserts the existence of all consistent mathematical structures. But that doesn't mean we can physically travel to or detect them. Critics argue that introducing an infinite number of unobservable universes to explain away specific puzzles, such as the fine-tuning problem, why our universe seems perfectly suited for life, or the quantum measurement problem, is akin to a cop-out or an intellectual sleight of hand. Instead of digging deeper for a fundamental explanation within our observable universe, the multiverse provides an external, untestable workaround. It essentially shifts the problem from why is our universe fine-tuned to why are we in the fine-tuned universe among infinitely many. While this satisfies the anthropic principle, it doesn't offer a mechanism for testing the overarching multiverse framework itself. It's a solution that, for some, feels less like a discovery and more like a retreat from empirical verification. Furthermore, there are philosophical objections, often invoking the principle known as Occam's razor. This principle, which advises us to choose the simplest explanation that accounts for the observed phenomena, suggests that positing an infinite number of complex universes, each as vast as our own, is an enormous ontological commitment. Why assume such immense complexity when a simpler explanation for the one universe we inhabit might suffice? If a theory requires the existence of vastly more entities than are strictly necessary, it should be viewed with skepticism. What could be simpler, the argument goes, than one universe rather than an infinite number of them? The burden of proof, in this view, falls heavily on multiverse proponents to demonstrate why such extraordinary assumptions are necessary. Another area of contention arises when we try to define what a universe even means in the context of a multiverse. If everything that could possibly exist does exist in some form or another across infinite realities, does the word universe still hold its singular meaning for our specific reality? If probabilities branch endlessly, or if all mathematical structures are equally real, what does it truly mean to be us in this particular, unique reality? Does it diminish our own significance, or does it merely redefine it within a grander tapestry? These aren't necessarily definitive refutations, but they highlight the deep philosophical challenges, the dizzying re-evaluations of identity and existence that come with fully embracing the multiverse concept. It's also important to acknowledge the practical difficulties. Even if some multiverse theories predict subtle, indirect effects within our universe, like specific patterns in the cosmic microwave background for cyclic universes, or gravitational leakage in brain worlds, these are incredibly difficult to isolate and measure. The noise of other cosmological phenomena, the limitations of our instruments, and the vastness of cosmic scales make definitive experimental verification an immense, if not impossible, task. The lines between what is scientifically testable and what remains purely theoretical speculation become incredibly blurry. Ultimately, the debate is robust and ongoing within the scientific community. While the mathematical elegance, theoretical consistency, and problem-solving potential of multiverse theories are undeniably appealing to many researchers, the lack of direct empirical evidence keeps them firmly in the realm of highly speculative, though profoundly intriguing, ideas. It's a question that pushes the very boundaries of what we consider scientific and challenges us to think about the nature of proof and reality itself. Until we find a definitive smoking gun, a piece of evidence that can only be explained by the existence of another universe, the multiverse will remain a captivating hypothesis, a whispered possibility, rather than a confirmed scientific fact. And perhaps, as you drift towards slumber, the lingering questions, the untestability of it all, will become part of the quiet mystery, allowing your mind to rest in the gentle uncertainty of the vast cosmos. And so, dear listener, we arrive at the quiet, contemplative close of our little voyage tonight. Or perhaps, as our cosmic musings might suggest, just another moment in the vast, looping, or branching sea of existence. We have journeyed through ancient quantum whispers, hinting at parallel branches where every possibility unfolds. We've soared through the cosmic froth of eternal inflation, imagining our universe as a single bubble among countless others. We've dipped into the subtle dance of brain worlds, where our reality is but a thin membrane floating in hidden higher dimensions. We've ridden the grand cosmic rhythm of cyclic rebirths, pondering universes that rise and fall like endless breaths. And we've even faced the most abstract and profound idea of all, a universe, and indeed a multiverse, fundamentally made of pure, self-existent mathematics. Along this expansive path, we've seen that the idea of another world isn't merely the stuff of fantasy. It emerges in different forms from the very equations and deep observations of modern physics, from the smallest quantum particle to the largest cosmic structures. We've considered the arguments for and against, acknowledging the tantalizing elegance of these theories while also respecting the rigorous demands of scientific falsifiability. No one has definitively proven the existence of parallel universes, and they remain, for now, in the realm of compelling hypotheses. But the questions they raise are among the most profound and fundamental in all of science and philosophy. They challenge our ingrained assumptions about reality, about uniqueness, about destiny, and about the very nature of existence. They force us to look beyond the immediate, to consider what lies just beyond the veil of our perception, or even beyond the very concept of perception itself. Ultimately, what we've discovered is that the concept of a parallel universe is not just one thing, but many. It is a quantum whisper, a cosmic bubble, a hidden dimension, a cyclical echo, a mathematical form. It is a testament to the human mind's insatiable curiosity, its ability to construct intricate theoretical frameworks that stretch beyond anything we can directly experience. And now, here you are, a little farther along your own timeline than when we began, perhaps with a slightly expanded sense of wonder, or perhaps a gentle hum of pleasant confusion in your mind. Was it seconds, minutes, an hour? Or did the flow of words and ideas stretch and shrink, accelerate and slow, like it so often does when the mind begins to soften, when thoughts begin to gently unravel and invite the approach of sleep? So let me ask you once more, gently, as I did at the start of our journey, where in this universe are you listening from tonight? Are you nestled in a familiar space, or perhaps somewhere new and intriguing? What time is it right now in your unique corner of the world, in your particular slice of this cosmic reality? Is it the quiet hum of the pre-dawn hours, or the comforting silence of late evening? And what little decision did you make today, perhaps so insignificant that it barely registered, that still whispers to you, even now, with the faint echo of, what if? Perhaps you turned left instead of right, chose a particular book from a shelf, or simply decided to listen to this voice. Funny, isn't it? After all this talk about countless realities, about infinite possibilities branching and expanding, we still anchor ourselves so deeply to this one, to the choices we make, the experiences we have, the memories we form, and the singular, precious timeline we inhabit. This anchoring isn't a limitation. It's the very foundation of our experience, our unique journey through this particular universe. If the multiverse is real, then our specific path, our particular sequence of moments, becomes all the more extraordinary. It's this one, with all its beautiful imperfections, its unexpected joys, its quiet sorrows, and its specific shade of cosmic light. It's the universe where you exist, right here, right now, experiencing this moment. And if you found any calm in this quiet expedition, if the wonders of the cosmos, however mind-bending, gave you a profound sense of peace, or if the challenging questions helped your thoughts to gently drift and guide you into your dreams, I'd be ever so grateful if you'd consider giving the video a like. And perhaps, if these sleepy scientific voyages resonate with you, if you wish to continue exploring the vastness of knowledge in a calming way, maybe subscribe to Cosmic Sleep. And if you know someone else who might benefit from a peaceful pause, from a gentle exploration of the universe's mysteries as they wind down, please consider sharing this sleepy space with them. The universe, whether singular or multitudinous, whether fundamentally physical or purely mathematical, is a place of endless mystery and boundless beauty. And right now, here in this quiet moment, it's just you, this voice, and the slow, steady rhythm of rest. May your thoughts be soft, your dreams be vast, and your sleep be deep and undisturbed. Sleep well, fellow traveler, wherever and whenever you are.